sound simulation, and we've done several things with it, starting with just figuring out what's going on here. Here's the sound waves, the zone of compression and the zone of rarefaction. We studied amplitude, which I want to emphasize again is basically the same as volume. It's the proper term for volume. We can also use amplitude for other kinds of waves, like on the lake. A high amplitude wave would be good for surfing, but not so good for paddleboarding. Because if it was high amplitude, it'd be waves that are really big. If it was low amplitude, it might have the same number of waves, but they wouldn't be so tall. Okay, so if it's loud, it has a high amplitude. If it's quiet, it has a low amplitude. But of course, sound waves don't actually move like this. They move back and forth, right? They vibrate this way. And that's what creates these zones of compression and the zones of rarefaction. Now, when it comes to frequency, that's how many waves there are. So, for instance, on the lake, if we had a high frequency of waves, there'd be a lot of them packed together. They'd be coming really quickly. But if we had a low frequency, there wouldn't be very many in the same amount of time, even if they were the same height. So the wave height gives the amplitude. The number of waves in an area gives the frequency. Now for sound, this means that we have a different pitch. And as we'll see after finals, for light, this means we'd have a different color. Like this would be blue light, and this would be red light. Blue light vibrates much faster than red light, for example. But for sound, a fast vibration, a high frequency, gives a high pitch. And a low frequency, a slow vibration, gives a really low pitch. Then we did this first lab, comparing the frequency, the pitch, to the time for 10 waves to go by. And you were supposed to make this graph. Let me know if you need help with that, because I turned you loose to do that on your own. Then in the second lab, which was last class, we compared frequency to the number of waves that went by. I asked you to count the waves, and then we calculated the hertz, and we compared how accurate we were to the actual number of hertz in the frequency. And that takes us to today. What we're going to focus on today is the speed of sound. How fast does sound actually go? How fast do sound waves move? Now, actually, it definitely depends on what material the sound is moving through. So, for example, sound moves through water much faster than it moves through air. And if you're underwater, like scuba diving or something, it becomes very difficult to tell what direction a sound came from because it goes so fast, the sound hits both of your ears simultaneously, and you can't tell which ear was activated first by that sound wave. But in the air, even though sound is fast, your brain can tell the difference from when a sound hits your right ear compared to when the sound wave hits your left ear. And your brain can calculate the difference without you even thinking about it, and you know that the sound was off to the right or off to the left. You can tell in the air because the speed of sound is slower. All right? So we're going to use the simulation to calculate the speed of sound. The way we're going to do that is at the top of this page is a ruler. Between the ruler that gives us a distance that the sound wave is traveling and the timer that tells us how long it takes to get there, we can calculate the speed of the sound. Distance divided by time is speed. And if you include a direction, then it's velocity. Okay? So we're going to just calculate the speed of sound by using that ruler and the timer. Measure the time it takes for a sound wave to move 5 meters by clicking start when the sound wave leaves the speaker and clicking stop when it arrives at the 5 meter mark on the ruler. So this is what we're going to do. For different frequencies, I'm going to click start and stop. And basically at the same time, I'm going to be watching one of these waves. So for instance, I would click start, follow this wave until it hits the stop. So what I'm going to be doing is holding my left finger over this speaker and moving my finger with the sound wave. When my finger arrives at the 5 meter mark, my right finger is going to hit stop. So I have to do two things at once. I have to follow the wave and click start. Follow the wave. When it hits 5 meters, I click stop. And then you're going to record this time. And we're going to do that 3 times for each frequency and take the average just to try to improve the accuracy. That's what it says in this sentence. Now, of course, before doing any good experiment, we should make a prediction. We should make some hypotheses. So what I want you to do is start by making 2 hypotheses. What do you think? Will a high frequency or a low frequency sound wave travel faster? So high frequency would be when it looks like this. They're shorter waves and there's a lot of them. Look how fast the speaker is vibrating. Compared to low frequency sound waves, not as many waves, they're wider. The speaker's vibrating much slower. Make a prediction. Do you think the high frequency, which is the high pitch, like from a flute, or do you think the low frequency, like from a tuba, which ones do you think will travel faster? Go ahead, write down your prediction now. Again, when you're making a hypothesis, the point is not necessarily to get the right answer, but it's just to predict what you think will happen. And then we compare what actually happened to your hypothesis, and it will either confirm your hypothesis or it might surprise you. And either way, we learn something, huh? So it doesn't matter if you're right or wrong, just that you think about it and make a prediction. Now remember, there's a third possibility. 3 possibilities in your predictions here. First, the high frequency could travel faster. Maybe you predict that. Maybe you predict that low frequency is going to travel faster. That's 2. The third one is that they could be the same. So what do you think? What will be the impact on the speed of sound when we change the frequency, the pitch? High pitch, low pitch. Predict what you think will happen. Then you're going to do the same thing for amplitude. High amplitude, in other words, a loud sound. In fact, maybe I'll write that down as a reminder. Do you think loud sounds or quiet sounds will travel faster? Or would they be the same? For frequency, this would be high pitch. In fact, one way to think about this would be treble versus low frequency, low pitch, or bass. Which ones do you think will travel faster? So while we're working on that, while you're writing out your prediction, I'm going to explain what's going on in this data table. So first of all, we're going to change the frequency, which of course is the pitch. Down here for 100 and 300, we would call that bass pitch. And up here for 700 and 900, we would call that treble, the high pitch. And we're going to do 3 trials for each frequency and find the average. So we will do 3 trials for 100 hertz. In other words, cycles per second, vibrations per second. We'll do 3 trials and then we'll take the average. We'll do 3 trials for 300 hertz and so on. 3 trials for each of these different frequencies, find the average. Now this top row is always going to be a low amplitude. It's going to be a quiet wave. And the bottom row, we're going to repeat everything except these are going to be high amplitude, in other words, loud. And the way that looks on our simulation, let me bring this up to like 500 just so we can see more waves. Here's high amplitude. And here's low amplitude. You can still see the waves, but there's just different amounts of gray here, huh? So in other words, these peaks and valleys are not that different from one another. Whereas here, where it becomes high contrast, there's a big difference in the black and the white. You can also see the speaker pumping a lot more. So predict what's going to happen when we change frequency and what's going to happen when we change amplitude, and give me a thumbs up when you're ready to move on. Thanks, Gus. All right, looks like a lot of us are ready to go. So the first trial, I'm going to set the frequency to 100 and I'm going to turn it quiet. All right, so let's bring this down to 100. Bring this down, not all the way because then it's turned off. Okay, so we're going to do this 3 times. You're going to write down the number that ends up being here. And I'm going to follow the wave for you from when it's released until when it hits the 5 meter mark, right? And I'm going to start right now on the back side of this zone of compression now. 0.0208. I know this is a tiny crazy number with that decimal in there, huh? So this goes here, 0.0208. Okay, we're going to do it again. We do it 3 times, then we take the average. I reset that. And now. 0.0182. This is why, you can see there's some difference between these, huh? And this is why we do it more than once. Probably the difference is because of a little error in my clicking. I'm either clicking too fast or too slow, something like that. It's hard to be accurate, and that's one reason we do multiple trials and find the average, because if I click too fast on one trial and click too slow on the other trial, they balance each other out. Reset this, get ready, set, go. $0.0202. Now you're going to need a calculator to do the next part. I'm going to do a couple with you, and then you're going to be doing them all on your own. So whenever we find the average, you take your numbers and add them together. 0.0208 plus 0.0182 plus 0.0202 equals. Add those 3 together, and then you divide by however many numbers you added in the first place. Since I added 3 numbers, I divide by 3. And I hit equals again. Now there's my final answer, 0.0197. And we want to take it out to 1, 2, 3, 4 decimals, just like we had in our measurement. So I look at this one, it's a 3, which is less than 5, so I just leave this as a 7. My average, 0.0197. All right. So get a calculator ready so you can do these other averages yourself. We're going to go back to the simulation. I'm going to reset it, and I'm going to take the frequency up to 300 hertz. Okay, and I'm going to follow this wave. We're going to do it 3 times. Here we go. Go. Oh, I lost track of which wave I was following. Sorry. Here we go again, and now. Stop. 0.0186. So that comes over here in the 300 section. And we're going to go again 3 times and then find the average. Here I go. $0.0190. So take this number and put it in the data table. Just to make sure you know what I'm talking about, it's going to go down here. It's trial 2 at 300, 0.0190. One more at 300 and quiet, huh? Here we are. And go. $0.0194. Now add those numbers together in your calculator and divide by 3. Clear what I had before. 0.0186 plus 0.0190 plus 0.0194 equals, divided by 3, equals 0.019. Well, that means I need to throw a 0 at the end of it. 0.019, and we just want that fourth decimal place. Now, if you don't think decimal places are important, I have a proposition for you. Since decimal places don't matter, I'm going to give you 1 penny, and you'll trade it to me for $100, because the only difference is the decimal place, right? Yeah. Decimals matter, so you got to keep track. You got to be really careful. Make sure they're in the right place, because otherwise, a penny is no different than $100. At any rate, let's go back to the simulation. We're going to go to 500 hertz now. The pitch is getting higher. I've turned the sound off. I just didn't want to listen to that little hum that it makes. But this, we would hear the pitch getting higher and higher here. So here we go. Trial 1, 500 hertz, quiet. $0.0190. Please record that on your data table. I'm going to reset it, and we're going to do trial 2. Here we go. Reset and begin. 0.0186. Third one. Oh, I lost track of which one I was doing. Sorry about that. Here we go. Zero point zero 186. So record those on your data table and please find the average for yourself and give me a thumbs up when you're ready to move on. Let me know if you missed some of those numbers and I can give them to you. Vanessa, it was 0.0186. So the second and third numbers were the same. Okay, so you should now have this part of the chart filled in, right? And we're moving on to 700. I'm going to reset this. I'm going to crank this up to 700. And just to make sure everybody's on the same page here, we'll look at this again. What are we on? Page 14. If you joined us a little late, we're on page 14. We made hypotheses about our predictions about whether the treble or bass would travel faster and about whether the loud or the quiet would travel faster. We're talking about the speed of sound here. And we're actually measuring it using this simulation. And we're going to do 700 now. Reset that. Okay, here we go. 0.0186. Record that in your data table. 700 hertz, trial 1. And we'll move on to trial 2. I'm going to reset it. Second one. 0.0188. And trial 3 for 700 hertz. Resetting, going. 0.0208. So record those in the data table. Add them together. Divide by 3 to get the average. Let me know if you missed one of those numbers because I wrote them down on my board, on my whiteboard behind me. All right, way to take care of each other, guys. Yeah. Excellent, Armando. Thanks for the help. And I also like the way Armando is referring to this as 186. It kind of is easier to think about it as 186 than 0.0186. That's why I'm kind of saying this every time with a pause. 0.0186. Because all of these numbers, as you can see, start with 0.0, huh? So when we're comparing them, if we just ignore that part and think of this as 197 and this is 190, it's going to be a little easier for us to think about these numbers instead of getting all tangled up in that 0.0 part of it. All right, I'm going to reset this. We're going to do our last quiet set. 3 trials at 900 Hertz. Here we go. Boy, it's hard to choose one to follow. (0.0192). I'm going to reset that and do trial 2. 192. Here we go, trial 2. (0.0180). All right, trial 3. Last one for the quiet waves. (0.0204). Okay, let's look at these averages for our quiet data. It's not going to allow us to compare the quiet to the loud yet. We still have to gather that data, but it already gives us an idea of what's happening to the speed of sound with frequency. The lower the number, the faster, excuse me, the higher the number. Nope, is that right? So when we're watching these go by, yeah, if it's a lower number, it's getting there faster, isn't it? So that should actually be a higher speed of sound with a lower number, right? It takes less time to get from point A to point B. It would be going faster, right? So the lower the number, the faster it is. And are we seeing a trend in the speeds? Are we seeing that low frequency is faster or slower than high frequency? And as it says down here, we are looking for major trends, not just minor details. Are we really seeing a big change in the average speed between these different frequencies? And if we are seeing a major change, which one's faster, bass or treble? Well, it seems to me that we never hit a number, and again, I'm going to refer to this as 197, basically 197, even though it's 0.0197. Think of this as 197, okay? So if this is 197, is that very different than 190? Is there a significant difference, or could the difference be more easily explained as a measurement error? Or is the difference actually there? Is it a true difference? Do we truly see them getting faster and faster as we go down here? I'm not sure what numbers you got down here because I didn't do the averages, but it seems to me that the lowest number we pretty much ever had was 0.0180. I don't even think we got down to 170 anything, did we? I think it was always 180, and the highest we ever had was something like 0.0 what? I don't even think we ever hit 210. weren't all, let's see, 15 of these measurements, 3 trials times 5 different conditions, weren't all 15 of those within this same range between 180 and 210? And if so, is there really any true difference in the speed of sound for bass notes versus treble notes? Or would it be more likely to explain these differences as a result of measurement errors on my part? Is there a true change in the speed of sound? Or is it more the way the experiment was set up and the way we gathered data that created inaccuracies in the data? And really, there isn't a significant difference, is the phrase that scientists would use. A significant difference. There might be a difference, but is it meaningful? Is it significant? Is it real? Or is it just a result of the way the experiment was set up? So that's something we're going to think about when we do the analysis in a minute. Let's go ahead and crank up the volume. We're going to repeat those 15 again, and we'll see if making it loud results in faster, slower, or waves of the same speed. Okay? So I'm going to crank up the volume all the way. It makes the waves actually easier to see. I kind of wish we'd done these ones first. I'm going to bring the amplitude down to 100 again. Reset the timer. I'm going to watch this wave leave the speaker, and I'm going to follow it with my finger until it hits the 5 meter mark. Here we go. .0196. So that's going to come down here now. 0.0196. Trial 1, bass note of 100 hertz, loud amplitude, 0.0196. Resetting that, going for trial 2. .0198. Record that on your data table. Trial 2, 100 hertz, loud amplitude, high amplitude. All right, resetting, third one. .0200. Go ahead and take a minute to find the average between those three. If you want a shortcut, don't even put in 0.0. Just put in 196, 198, and 200. But when you write down your answer, you have to put 0.0 in again. But a shortcut on the calculator, you can skip the 0.0 in the front and just put in those other 3 digits. You can't skip these 2 though. Those have to be there, even though they're zeros. You would have to include those in the calculator if you're doing it this way. 196 plus 198 plus 200 divided by 3. All right, I'm taking it up to 300 hertz. I'm resetting the clock, and we're going to follow these higher frequency waves. They're still bass notes, but they're not quite as low as the other ones. .0198. Get that on your data table, and we'll do trial 2. Here it comes. .0204. Okay, third trial at 300 hertz. Here we go. (0.0206). Okay, so what do we have? 198, 204, and 206. Add those together and record your average down at the bottom, right? Add them together, divide by 3. I'm going to get ready for our next set. Please let me know if you need any numbers repeated. We're moving on to 500 hertz. I'm going to start the clock and follow the wave to the 5 meter mark. (0.0190). Okay, second trial. (0.0198). And the third trial. (0.0194). Add those 3 together, divide by 3 to get the average. I'm going to move this up to 700. Higher frequency waves coming through. You can see frequency basically means how often something happens, right? And look at how often there's a wave created. That's another way to think about it. If it's a high frequency, there are many waves coming through. They go by very often. The vibration is happening quickly, so we get a lot of waves. They're very frequent. If it's a low frequency, they're not very often. They're released more infrequently, I guess you could say. Anyway, we're supposed to be at 700. And here we go with trial 1 for 700. (0.0188). Record that in your data table. Okay, I'm going to reset that and do trial 2. (0.0200). And here we go for the third trial on 700 hertz. (0.0194). All right, almost done with this lab. At least with gathering data, then we have to analyze it. So we're going up to the highest frequency, the highest pitched sound. I'm going to reset it. We're at 900 hertz. Oh, I want to give you a moment to calculate your average. Sorry, I'll wait. Okay, let's go ahead and do trial 1. Oh, I forgot to hit start. Try again. $0.0180. And I'm going to reset this. Trial 2. $0.0198. And the last one. $0.0194. So find that last average down here, and your data table should be complete. I actually wrote down all of this data. I don't have this data actually, but I do have this data written down for the loud amplitude, for the high amplitude. So let me know if you need one of these numbers. I wrote it down on my board and I can give it to you if you missed something. So just let me know. And give me a thumbs up when you're done with that and ready to move on to the analysis. Thanks, Vanessa. So what we need to have is 10 different averages now, right? This is what's going to be important. And you could see why we were doing the average, because when I measured it, it often came out pretty different one from another, huh? 208 versus 182, for example. So this is why we do averages, is to get rid of little inconsistencies in the way that we gathered the data. An over measurement will be canceled out by an under measurement when we do these averages. So that's what scientists are going to do. Of course, they might do this not just 3 times, but 10 times, 100 times, something like that. So, part 1 of the analysis. Did high or low frequency waves travel faster? And please explain your answer. Again, we're looking for major trends, not just minor details. Did you actually see that the speeds got faster and faster or slower and slower? And remember, I'll write it down up here. Or maybe I'll just put it here. That faster equals a lower number because it took less time to get there. Faster would be a lower number. So just comparing the two averages that I do have written down, we would say that 300 was slightly faster than 100. Did that trend continue on and on and on across all the frequencies? And if so, we should see it repeated both on this row and on this row. Do we see it getting faster and faster and faster? And is it significant? This is another really important phrase in science, is a significant difference. Was there a significant difference between these different speeds of the sound waves? It'd be great if you use that as part of your explanation. You could say there was a significant difference. You could say there was no significant difference. For example, this is so important in science, and it's relevant to what we're experiencing in our lives with coronavirus and the vaccine. Is there a significant difference between people who receive the vaccine and people who don't receive it? Was there a significant difference in the amount that they got infected? And they tested it on something like 50,000 people. And they found that there was a significant difference where people that got the vaccine were 95% less likely to get infected than people who didn't get the vaccine. A 95% difference, that's pretty significant, isn't it? So did high or low frequency waves travel faster? You're comparing across the chart, and you can do it twice. And then, did high or low amplitude waves travel faster? Now you're comparing up and down. Did we see a difference in these? And if there was a difference, was it significant? Were the loud ones always faster than the slow ones? Excuse me, were the loud ones always faster than the quiet ones? Or were the quiet ones always louder than the loud ones? Or was there no significant difference? Were they all about the same? Again, from what I seem to have noticed while we were gathering our data, was that every time the number ended up somewhere in here between 180 and 210. And I'm guessing most of your averages are in the 190 something range. So is there really any difference in the speed of sound for a quiet sound or a loud sound? Is there really any difference between a high-pitched and a low-pitched sound for how fast the sound waves is? And I hope you agree with me that there was really no significant difference for either pitch or volume, for either frequency or amplitude. Really, there was no significant difference. Pretty much always the same. And let's think about if this makes sense. Let's say you're at a football game and you're sitting up in the stands and the marching band is playing down on the field. Here's the tubas making all these bass notes, low frequency sounds, and here's the flutes making all these high frequency treble notes. Now when the tuba and the flute are playing together and that sound leaves the instrument, crosses the field, goes up the stands, and then hits your ear, are those sounds separated, or do they reach your ear at the same time? Or you're at a concert and there's this throbbing bass, right? There's this bass line that goes along, boom, 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 boom. And in between that, there's the treble line. Do those get separated when you're close to the band versus when you're far away from the band? Or do they stay together relative to one another and the rhythm is maintained no matter how far away you are? That's what happens, right? Bass notes, treble notes, high frequency, low frequency, they travel at the same speed. Let's look at that. Here's high frequency, and it looks like it's going so fast. It is pulsing fast, isn't it? Lots of vibrations, but if you watch these waves, and then I take down the frequency, you'll see that my cursor moves at about the same speed. regardless of whether it's high or low frequency, it's moving at about the same speed, right? So the speed is not changing, but the number of waves is definitely changing. It's vibrating much faster, but that doesn't mean that the wave is moving any faster. They're all in the 190s, huh? And the same thing was true for loud and quiet. It doesn't matter if it's loud. When I drag my cursor along with the wave, it's moving at about the same speed. Whether it's loud or quiet, it doesn't matter. It's moving along at the same speed. So hopefully you use this phrase, significant difference, to explain your answer between pitch and volume and how fast they move through air. That takes us to question 3, and we're going to work through this together. The actual speed of sound is about 750 miles an hour, and we're going to compare our measurements to the actual speed of sound. So I want to think about this 750 for a minute. So we call the speed of sound about 750 miles an hour, and when they invented airplanes and then they invented jets, these were flying slower than the speed of sound. A typical passenger jet today, like a jet that you might take to on vacation somewhere, is going to be going less than the speed of sound. It might be around 300 or 400 or 500 miles an hour. But some military aircraft can fly faster than the speed of sound. And at first, when they were inventing these jets, they were trying to break the sound barrier, they called it, because no one had gone faster than sound before. And in fact, they didn't even know what would happen. It was a bit of a risk for the test pilots who were going to fly these first jets faster than the speed of sound. They knew that the machine could go that fast, but they didn't know if the sound vibrations would tear it apart when it went that fast. Like when they're going 800, 900, 1,000 miles an hour, they cross the sound barrier. And basically what happens, because they're moving so fast, when they cross this barrier, it makes a big boom. It makes a big sound that sounds like an explosion, and they call it a sonic boom when something goes faster than 750 miles per hour. I heard one once here in Tahoe a few years ago. There was this massive explosion sound early in the morning. It was like 6 a.m. and I'm like, what was that? And it went echoing around the whole basin. It turns out later they discovered it was a meteor that came into our atmosphere probably at 10 or 15,000 miles an hour, and it made a huge sonic boom that sounded like an explosion when it went through the air. Actually, they found the meteor. It was south of Tahoe, maybe 50 miles or something. It hit the ground. Okay, so what we're going to do is we're going to find the overall average. What I mean by that, since there is really no difference between these different measurements, we're going to combine them all together. So I want you to take your 10 averages, take those 10 averages, add them together, and divide by, this time, since there's 10 of them, you divide by 10. So please find your overall average for these 10 measurements, and when you get it, please post it on the chat. Find the average of the 10 averages, which will give us the average of 30 measurements, because each of these was the average of 3, huh? So find the average of those 10, add them all together, divide by 10, post it on the chat. No, I don't have a video of the meteor, Armando. That'd be cool if we did, but no video available, I'm afraid. I have seen videos of other meteors though. There was a big one that came down in Russia, and it was over a city, and so people that had dash cams, if they had a camera on their dashboard, they actually filmed it coming down, and I think it included the sound that it made when it broke the sound barrier. I think it was such a big sound that it created these huge vibrations, and it rattled windows and might have even broken some windows. Please post your average of the averages when you get that. And then what I'm going to do is I'm going to take the average of the averages of your averages, and we'll get an overall combined number. So post your overall average once you get it calculated. Add them up, divide by 10. Thanks, Quetzali. All right, guys, thank you very much. You guys are way more consistent than my third period class. They had a lot of variation in their averages, but yours are all very close to one another. And I think I'm just going to work with these 7. So I've added them up. I divide by 7. And my answer is 0.0194. So I'm going to put that in here, which is basically what most of you guys got, huh? Now, we're going to convert this into miles per hour. And it's kind of weird because this was not even meters per second, but that was in 5 meters. That was seconds to go 5 meters. So there's a couple things we have to do. We have to get rid of the 5 in the 5 meters, and that's part B. And then we have to convert this from seconds per meter to miles per hour. So here's what we're going to do. We're going to take 5 meters divided by your average. So I'm going to clear this. I'm going to put 5 in there, and I'm going to divide by 0.0. Now, it's important you include 0.0 now. And I get 257.73. Since that's a 3, I just leave the 7 alone. 257.7. Is that what I had? Oops, I don't need that anymore. Yeah, 257.7. Now, to convert this to miles per hour, I take this number, and I'm just going to leave this whole thing in my calculator, and multiply by 2.237. This is just a conversion factor, and it has to do with how many meters are in a mile and with how many seconds are in an hour. So you don't have to worry about where I got that number from. It's just a conversion factor. Just like to convert feet to inches, you multiply by 12. Or to convert inches to centimeters, you multiply by 2.54. In this case, to convert meters per second to miles per hour, we multiply by 2.237 equals, and there's my answer, 576.5 miles per hour. Okay? Now, how does that compare to the actual speed of sound? Remember, the actual speed is 750. And here, I calculated 576. So what does that tell us about how accurate my measurements were? Well, let's find our percent error first. We know that there's error in measurement, so ideally, if we did a good job on making our measurements, ideally, we would have, I'm going to call it an ME, a measurement error, that was less than 10%. The smaller, the better for measurement error, and we can really trust our data if it's within 10% of the known values. So let's see how I did. To find percent error, I need to do some calculations. So let me see, I'm going to clear everything again. Subtract your speed from the actual speed. So I'm going to put in the actual speed first because it's from the, so that means I have to put in 750 first. Then I subtract my speed, 576.5. I hit the equal sign and I divide by the actual, 750 equals. My percent error was, well, remember, to get percent, you got to multiply by 100. My percent error was 23.1% off. 23.1%. That was my percent error. Okay? Again, ideally, we would like to be less than 10% to really be able to say, yeah, I did a good job on my measurements. We'd like to be within 10%. So my measurements were maybe not so good. However, I do think that they showed what we were looking for, which was the speed did not change very much when we changed frequency. It also did not change very much when we changed the volume. It was always around 190, 195. So what you're going to do is describe your response to this accuracy. Okay, you're going to write something about that. Don't start now because we're going to finish up class here. I'm going to tell you what I'd like you to do on your own. Then we get to the summary for these three labs. So these questions on page 15 will include things going all the way back to the beginning of this lab. So remember, the lab had an intro section right here on page 10. So there will be some questions from the introduction on the summary. So you'll want to go back to page 10, and 11 has some more of the introduction. Then on page 12, we had our first lab. Page 13, we had our second lab. Page 14, we had our third lab. So page 15 has 8 questions. And it could refer to any of those pages that have to do with the lab, but it won't go back before the lab. Then the only thing left on this whole project is a final conclusion and a review of the entire project. So now we could go all the way back to the very beginning for these final conclusions and review. It could take us all the way back anywhere in the project for the last, page 16, 17, and 18 to finish up the project. I'll give you a hint, like describe how either an animal or a piece of technology uses ultrasound or infrasound. And that was discussed way back here in this reading on page 4. Ultrasound and infrasound. So you might have to refer back to earlier things that we did. Now, one thing I would like to do before I turn you loose is talk about ultrasound, infrasound, and human hearing a little bit between 20 and 20,000 hertz. So I have a nice diagram here showing the different frequencies of sound. And again, frequency is how fast it's vibrating. Hertz means vibrations per second. So notice that this chart goes from 0 hertz, no vibrations. It goes all the way up to 200 gigahertz, which would be billion vibrations per second. 0, 20, 200, 2K, 2,000 hertz, 20,000 hertz. Notice number 9, this is the range of human hearing from 20 to 20,000, 20 to 20K. So if you're ever like shopping for speakers or headphones, you should look to see what its frequency response is. What is its range of frequency? If it only goes from 200, you're not going to get these bass sounds. You're not going to hear the lowest bass sounds that are part of the music. If it only goes up to 10,000, you're not going to hear all the treble. But if it goes beyond 20,000, let's say it goes to 100,000 and they're like, oh, look how far this goes up. Well, you can't hear that anyway. You can't hear beyond 20,000. So why pay money for speakers or headphones that go up to 100? You would never hear a frequency beyond 20,000. You don't need to pay for headphones that go up to 100,000. Similarly, on the low range, you want it to go down as far as 20, but below that, you wouldn't hear it anyway. Now, this might be a little different for a subwoofer. Like if you want to put a subwoofer in your car, you wouldn't hear any sound below 20 hertz, but you might be able to feel the vibration down at 10. You couldn't hear it, but your body could feel that vibration. So for a subwoofer, maybe you want to go below 20. But you know, when it's vibrating this fast up here, you wouldn't even feel it. So it wouldn't make any sense to spend extra money to go beyond 20,000 hertz, 20 kilohertz. So humans hear from 20 to 20. Below that, we call it infrasound. Infra means below. And above that, we call it ultrasound, which means over or above. This is above human hearing. This is below the range of human hearing. Now, there are vibrations that are this low, like earthquakes set up vibrations in the infrasound range, and a seismograph can detect those. The same thing is true for a nuclear bomb. When it explodes, a seismograph can detect that. So we can actually tell if people are doing atomic bomb tests by using our seismograms that normally just measure earthquakes. We can recognize if someone has detonated a nuclear bomb and tested it underground. Even if you couldn't see the mushroom cloud, we could still tell that they set it off because the vibrations, these really slow vibrations, get picked up by a seismograph. Next, it talks about acoustic. That's just the proper name for the range of human hearing. If it's in the acoustic range, it's between 20 hertz and 20,000 hertz. We often just say 20 to 20 or 20 to 20K. Animals, however, can hear what we can hear, and some animals can hear higher pitches than we can, like dogs. Like you can buy a dog whistle that when you blow on it, seems to make no sound at all because it's beyond the range of our ear's ability to pick it up. But the dog can hear it. It has the ability to hear those high-pitched sound. The same is true for bats. They can hear these ultrasounds and they use them to navigate and to find their food in the dark. On the other hand, some animals can hear below what we can hear. Like elephants can hear infrasound vibrations, and they communicate with each other, sending out these really low-pitched, ultra-bass subwoofer sounds that carry for miles across the savanna or through the jungle. So they can actually be in contact with one another, even though they're a mile apart, by creating these infrasounds. When we discovered this, oh, and here's another crazy thing, we think they pick up some of these infrasounds with their feet. It's more like they're feeling the vibration than actually hearing it. But when we discovered this about elephants, that they use infrasound to communicate and they're sensitive to it, it made us a little worried about them in terms of the ones that are in zoos, especially if they're in a city zoo Imagine if there's a freeway going close to the zoo and all the vibrations being created by cars, and how that could be transmitted as infrasound right to the elephant. A big truck goes by, it vibrates the freeway, that infrasound gets picked up by the elephant's feet, and it's driving the elephants nuts that are in captivity. So that's a little concern. Up here in this ultrasound range, we have ultrasonic cleaning. Like if you've been to the dentist and they've used the ultrasonic cleaner. I know my wife is a dental hygienist and she uses an ultrasonic to clean people's teeth. These really rapid vibrations break the plaque off your teeth, but they leave the tooth intact. It vibrates at like 30,000 hertz, 30 kilohertz, high vibration. We can also use ultrasound for medical testing in this entire range of vibrations. Maybe you've heard about a pregnant woman getting a sonogram. Sono means sound. What they're doing, and maybe you've seen this on video too, they expose her belly so her skin's showing, and then they put this device on her belly and they roll it around on her belly. It is sending high vibration sound waves through her stomach and through her organs and through the fetus. And then when those sound waves bounce back to the detector, they're converted into an image. So we're taking these high frequency sound waves, ultrasound, and we're converting them into a visual image, and it shows us a picture of the fetus even before it's born. We can also do this with really high frequencies, and again, the higher the frequency, the tinier the wave. These waves are so tiny we can use them as a microscope. It's literally a sound microscope. We can look at very tiny objects if we convert those sound waves into a visual picture. So this is the entire range of sound, but this is all that we can hear. We only experience a part of the world of sound. And as we'll see after finals, the same is true for light. We only experience a part of the world of light. So the last 3 pages are review questions and summary questions. The last one is like diagrams of sound waves. We're going to talk about some of these next class when I see you next week. But I want to offer you the chance to finish this whole thing on your own for extra credit. If you have this entire project turned in before I see you on Tuesday, I'm going to give you the extra credit bonus. All right? So finish everything else yourself. Finish the summary yourself for the sound labs, and then the final conclusions and review for the entire project. Get that done on your own, and you're going to get extra credit. But I can help you with it along the way, and I will be helping most people, especially for some of the math problems, I imagine, on Tuesday and Wednesday. These questions 3 and 4 have to do with octaves. And just to, if you want to try to get that extra credit, just to remind you, an octave means it doubles the frequency. So if you go up an octave, it doubles it. If you go down an octave, it halves it. So for example, standard concert tuning is 440 hertz. That would be the note A. The next A up, the next A up, you double that and you get 880, and that would be a higher A. If you want to go to a lower A, you divide by 2. What would that be? 220, huh? So these are all A's. As long as they're doubled or halved, it's still an A. Okay? So that's all I have for you today. Please work on this on your own, finish it for extra credit, and I will see you in the classroom next week. That'll be great. Again, you'll be in the building 2 days and out of the building 2 days. You'll alternate like that for the rest of the year. Okay, let me know if you have questions, if you missed some of that data. Stick around. Otherwise, we're done. And I hope you have a good weekend. Celebrate Martin Luther King Day.
All right, Fairley, you have a good day.
You too.
Thanks, Fairley.
Thanks, Fairley.
Bye.
Thanks, Fairley.
See you, Fairley.